So this lesson is all about weak acids and bases, and it also covers Ka values and Kb values. Now, I've just put up some definitions of acids and bases, and there's three definitions that exist for acids and bases. The first is an Arrhenius acid and base definition, where acids donate hydrogen ions and bases donate hydroxide ions. An example of an Arrhenius acid is HCl, and an Arrhenius base is NaOH. Now, it's not the best definition because it doesn't incorporate all the substances that act as bases. And so Bronsted and Lowry simultaneously came up with a better definition for acids and bases. They kept the definition for acids donating hydrogen ions, but they changed it so that bases are accepting hydrogen ions. This is sometimes also written as donating protons because a hydrogen ion is simply a proton. Now in this definition, HCl would still be an acid, but it allows us to add NH3 as being a base as well. So it's a much broader definition. Lewis acids and bases is the most broad definition, and it says that acids accept electron pairs and bases donate electron pairs. So I just fixed that typo there. So bases donate electron pairs. Now this means that substances like BF3, which normally would not have been considered an acid, can now classify as being acids. And things like NH3 are still bases. So the definition for Lewis acids and bases is a more broad definition, but we don't tend to use it as often. We tend to stick with the Arrhenius definition and the Bronsted-Lowry definition. So this was review. The new stuff starts to talk about weak acids and weak bases. Now the difference between a strong acid and a strong base is the amount that the acid is able to dissolve or ionize. A strong acid is going to separate all of the HAs into H plus and A minus. So then in this example here, all of the H's and A's are separate. In the weak example, almost all of the HAs stay together and only a few of them separate. And that's the difference between a strong acid and a weak acid. Now, this is not to be confused with the terms concentrated and dilute. You can have dilute strong acids and concentrated weak acids. They're talking about different things. So the important thing to realize is that weak acids are not going to ionize as completely as a strong acid. Often strong acids are shown with only a single-headed arrow in the forwards direction. Now, we can describe the acid strength in various ways. We can describe it by the Ka value. Big Ka signify strong acids, while small signify weak ones. The position of the dissociation. Strong acids favor the forwards reaction, versus weak acids favor the reverse reaction. And so you have a lot of reactants for the weak and a lot of products for the strong. Or you can do it by comparing the concentration of the hydrogen ion at equilibrium with the HA that you started with. For a strong acid, those two values are going to be almost the same. For a weak acid, the amount of HA that dissolves is very small, so the concentration of hydrogen ion is small when compared with the initial concentration. Alright, so a Ka value is constructed in much the same way that you would construct a Keq. It's a way of describing how weak or how strong the acid is, and we call a Ka the acid dissociation constant. The smaller your value for Ka, the weaker the acid is. And so this is just a generic acid, HA, dissolves into H plus and A minus. And so we do products, and they would be raised to their coefficient, if there was one, over the reactants raised to their coefficient, if there was one. Now you would construct a Kb the same way. Kb's are for bases, so they'd be called a base dissociation constant. Percent ionization is another way of describing the strength of an acid. The percent ionization formula is provided here, and it's the concentration of hydrogen ion at equilibrium divided by the initial amount of your undissociated acid. multiplied by 100. And again, the larger this value, the stronger it is. Strong acids have almost 100% ionization versus weak acids that are usually really very small values. All right, so this is a sample problem involving acetic acid, which is a very common weak acid. And in this 0.10 molar solution of acetic acid, it says that the hydrogen ion concentration after it had dissolved was 1.34 times 10 to the negative 3. So I already filled in my initial value of my acetic acid undissociated, the amount that had dissociated initially, so that was 0, and the amount at equilibrium. We also, I also wrote my dissociation equation and my Ka expression. So now what we're going to do is fill in the information we know. We know that the H plus and the CH3COO minus have to increase. And we know that the amount of acetic acid together is going to decrease. We also know that it's a 1-to-1-to-1 ratio, so these are all going to change by the same amount. Since I know that the hydrogen ion started at 0 and ended at 1.34 times 10 to the negative 3, that's our change. So 1.34 times 10 to the negative 3 for each of these. Which means I can find my value at equilibrium for each of these. This one comes out to 0.0987. And this one's just going to be 1.34 times 10 to the negative 3. Now it asks for the value for Ka, so I'm going to take my equilibrium values and I'm going to plug them into my Ka expression. And once I do that, it's going to be these values, 1.34 times 10 to the negative 3rd squared over 0.0987, and this comes out to 1.82 times 10 to the negative 5. And that's our value for the Ka. Now, another thing that we do is we tend to tie Ka values and Kb's with the pH at equilibrium. And so I just wanted to include this slide which talks about the relationship between pH and pOH and the concentrations of H plus and OH minus. This is all review, but I thought it might be useful to have it with your notes here. So we have pH, H plus, OH minus, and pOH, and they're all connected using the various formulas around the square. We know that pH plus pOH is 14. We know that pH is the negative log of the hydrogen ion concentration. If you multiply OH and H plus concentrations, it's 1 times 10 to the negative 14. And if you want to find the H plus, you just do the opposite, which is 10 to the negative pH. The other useful piece of information is this down at the bottom, that when you have a neutral solution, that means that the moles of H plus and the moles of OH minus are equal to each other.